Thanks for the introduction. Hi, my name is Jason McDowall. I'm a VP at Ostendo. At the dawn of the photonic era, Ostendo is a hardware technology company dedicated to making light smarter and more useful. I'm also the creator and host of the AR Show podcast, where I've shared more than 100 episodes of in-depth interviews with entrepreneurs, executives, and other thought leaders across the industry. The co-founder and CEO of Ostendo is Dr. Hussein El-Ghorori. Hussein is a visionary leader who brings decades of experience developing cutting-edge microprocessor and radio technologies to a new domain. At the start of this endeavor, he asked, how do we solve the last 30-centimeter problem? Now that we have computers in our pocket with high bandwidth connections to the internet, what's the best way to get that information from the device into our brains where we can enjoy it or act on it? To give you a preview of the punchline, Ostendo has created the world's first and only full-color, highly manufacturable, LED-based microdisplay. I'll get into some of the architectural details and show it in action, but first, I'm going to set the stage a little bit. We're all attending AWE because we have a shared belief. We believe we are fundamentally visual creatures. We think in 3 dimensions and we live in a physical world. This presents a tremendous opportunity, the opportunity for information to break the plane of the 2-dimensional screen in our hands or on our desks and fill the world around us to give us hands-free, highly contextual, and timely insight. Our collective pursuit of this goal didn't begin recently. It began 60-some years ago. You may be familiar with the Sword of Damocles. In 1968, Ivan Sutherland, the quote-unquote father of computer graphics, published his paper about a head-mounted 3-dimensional display. That system was the first documented optical see-through augmented reality solution. He demonstrated the idea of overlaying digital information on top of the physical world. After that incredible burst of innovation in the 1960s, progress was slow for the next several decades, at least as it relates to AR. 25 to 30 years later, in the mid-1990s, the industry was exploring AR in university and corporate research labs. Boeing was particularly active. Through their experimentation and imagination, these researchers envisioned many of the early use cases for AR that we still talk about today, including remote collaboration, guided instruction, and data visualization. But these systems were expensive, custom contraptions that merely teased the potential for AR. Here we are another 25 to 30 years later. We've seen some engineering marvels that shrunk those earlier contraptions into devices that can actually be worn on the head, including the standalone HoloLens 2 and the smartphone companion devices, the Emerald Light and the North Focals. It feels like we're on the cusp of wide-scale enterprise adoption and even a consumer-acceptable device. But we still have a few hurdles to overcome to make these truly all-day wearable devices. One way I like to break this down is to group the challenges into 3 main buckets. One of these is the visual quality. The intention is to be able to see clearly both the digital information and the physical world with no compromises. Of course, this one bucket is itself composed of many subcomponents that often fight against each other. Improving one causes another to get worse, such as the trade-off between field of view and angular resolution. Another bucket is comfort. This covers physical comfort, including weight, heat, and ergonomics, but also covers the social comfort in wearing the device in public. And a third bucket is the context of the information being displayed, enabling it to be timely and relevant. Here I lump everything from the sensors focused on us and our environment to the system's ability to recognize or anticipate our intention. Ideally, a device maxes out on each category, but the reality is our best efforts to date still have a long ways to go, particularly for consumer-grade devices, and each increment along the axis requires a tremendous amount of effort. And while there are a lot of challenges here, many of them are tied to the visual engine, either wholly or partially. The visual engine is the system for generating, modulating, and redirecting the light, the photons, into our eyes and combining it with the photons from the real world. Unfortunately, the ways we've been generating light for the last 150 years don't really work well. They don't solve the tricky set of problems that need to be resolved to create a socially acceptable head-worn device. Another quick dip into history here, going back to the invention of electron beam scanning and cathode ray tubes, it has traditionally taken decades from innovation to commercialization. For example, CRT technology was conceptualized in the late 1870s, practically demonstrated in the late 1890s, and commercialized in the late 1920s, early 30s. And then it sat on our desks for another 70 years. Other technologies, including DLP, LCD, OLED, and laser scanning, followed similarly lengthy paths from conception to commercialization. And all these technologies were also miniaturized and used in head-mounted displays over the last several decades, although with many shortcomings. As a side note here for the casual listener, reading the marketing materials for some companies about LED displays can be confusing. Some displays use LED as the backlight for an LCD, and they refer to them as LED TVs. But they're still liquid crystal, albeit brighter and more efficient. Others tout micro-LED TVs, but their definition of micro is at least 2 orders of magnitude too large for AR glasses. Unfortunately, making a technology work in a smaller package isn't always just a matter of money and elbow grease. While we can point to microprocessors and cite Moore's law for the last 50 years, even creating tiny transistors in silicon has its limits, and Moore's law doesn't apply to displays or optics. Light is especially unruly. The billions of dollars being thrown at these problems by some of the world's largest companies is a good indicator of how difficult it can be. Every component, every interface in this process is fraught with peril, especially when trying to make something both small and efficient. For the sake of time here, I'm going to skim over the impacts of Lambertian emission, which include the fact that photons spray out of atoms in random directions, so that light needs to be corralled, as well as the impacts of étendue, which includes some very hard trade-offs between the size of a lens used to corral that light and how random the light is coming out the other side. More orderly light requires a bigger lens, which isn't what we want in a small headset. The bottom line here is any attempt to control the light after it's emitted has many undesirable side effects in a wearable display. One thing is clear to me: while they each have their strengths, these existing display technologies are not the path to creating truly wearable, consumer-grade devices. I don't have time to go into all the details here, but the bottom line is there are too many inefficiencies and negative impacts to the visual quality. That's why we believe as a company, that inorganic LED-based solution is the right path. And we're not alone in that thinking. Facebook's recent tie-up with Plessey and articles written by display and optics expert Carl Guttag on his blog both suggest the same. But at Ostendo, we're not just building a tiny display that puts out multicolored light. Our founder, Dr. Hussein Al-Ghorori, began tackling the problem from a different perspective. Fundamental to Ostendo's approach is an appreciation for the human in the loop and an attempt to match the transmitter, the display, to the receiver, the human brain. We as humans have eyes that are exposed to an incredible amount of information, and all that information, as it enters our eyes, it's compressed down to just a few kilobits. That compressed input is all our brains require to understand the world around us. The compression that's happening is partially a function of the sensor distribution across the back of our eyeballs and how those sensors are excited. We perceive most of the color and high-resolution detail only through the cones at the very center of our eyes. The rest of our vision is covered by rods, which are good for low light and motion sensing. The compressed input is also a function of how the brain stitches together the information to form our perception of reality. The brain is telling the eyes to jump around from spot to spot to fill in details in what's called a saccade. And it does this several times a second. The brain plans ahead, ignores the moments when the eye is in a saccadic motion, and then backfills the information after the eyes come to a rest. And in doing all of this, it does a brilliant job of taking in just a few kilobytes of information and convincing us that our entire visual field is colorful, high resolution, and always up to date. To have a fighting chance of enabling a truly wearable device, the display solution needs to take full advantage of the shortcuts used by the human visual system. An ideal solution only puts visual data where it's useful to the eyes and our brains. And while that certainly includes full color, high angular resolution, and high brightness, it also includes dynamically adjusting the information coming from the display, including the color gamut and the amount of detail based on where the eyes are looking at that moment in time. That's the solution we're creating at Ostendo. Our approach involves the creation of a novel architecture for generating and controlling photons. Some might call this a monolithic micro-LED display. We call it the QPI, the quantum photonic imager, because it's so much more than a simple full-color light emitter. It's composed as a 3-layer sandwich with a control layer at the bottom, the photon generation layer in the middle, and an optics layer at the top. The base layer is more than just a simple backplane. This silicon CMOS layer is an advanced multi-core parallel processor that is able to operate on compressed input. It enables response times up to 5 nanoseconds and an adaptive gamut. This allows the imager to be responsive to eye movement and match the color gamut and level of detail that the human vision can actually perceive in different parts of the field of view. The middle layer is composed of 3,5 materials, specifically gallium nitride and its composite alloys. That's the LED part that when it gets excited, it releases photons that we can see. In our first generation device, this layer is made of bonded red, green, and blue layers that are vertically stacked. As a result, full color RGB is emitted from each aperture. Plus, we're able to achieve a 90% fill factor, which means 90% of the surface of the chip is able to produce red and green and blue. When all the colors come out of the same spot, this gives the QPI a distinct advantage when integrating with optics and minimizing the negative consequences of making really tiny pixels that are close to the size of the wavelengths of light. And speaking of optics, the top layer of the QPI is an optics layer, which uses nano-imprint dielectrics. It enables the light to be polarized at the source and the stream of photons to be collimated. This enables even more efficient integration with combiner optics. The optics layer also allows for the direction of the light to be different for each pixel, which becomes useful when we want to create a light field. I'll touch on that a bit more later. And the whole pixel assembly is only 5 to 10 microns, enabling 10,000 to 40,000 pixels per square millimeter. The overall result is a technology that can deliver better visuals matched to the human visual system, and it can deliver better efficiency, enabling the resulting device to be more comfortable and more wearable. And the beauty of this approach is it utilizes semiconductor manufacturing tools. Every piece in the process is compatible with high-volume manufacturing. Here it is in action. The imager is attached to a flex connector, which is laid out on a bench, and driven by a device streaming the trailer to Angry Birds over the MIPI protocol. As you can see, the display is tiny. That's an actual dime. The chip itself is maybe half the size of my pinky fingernail. Here's another view, zooming out a little bit. These two QPI are on a flex connector and are destined for a pair of demo glasses that are wirelessly connected to a smartphone. But that's not all. Because of its size and optical attributes, we can place the QPI right up against the edge of the lens. The QPI can be optically coupled directly to a custom lens designed by Ostendo and made from lightweight plastic. And we can tile them to expand the field of view. This 3 QPI arrangement per eye can deliver a 150-degree horizontal field of view. We aren't ready to talk about the details of how the combiner optics work here, but it's something we're developing. The designs allow for the lens to be curved to conform to the shape of our face, and it wouldn't block our vision as some other AR solutions do. To take it one step further, Ostendo is building this into a full reference design to showcase its capabilities. To give you a peek further behind the curtain, Ostendo is actively pursuing a number of additional complementary innovations. One of them is around the science of making LED materials. Rather than use 3 separate LED layers to make red, green, and blue, Ostendo is working towards using only one. We've demonstrated a monolithic, color-tunable gallium nitride-based LED structure which uses selective quantum injection to generate all 3 primary colors from a single material. Those images are photos taken of the LED material in action. This color-tunable LED is one path to achieving smaller pixel pitch sizes, and it will simplify the manufacturing process. Ostendo is also working on a highly efficient eye position sensing and prediction solution, which will complement the QPI's ability to dynamically adjust the information being transmitted to the eyes, among some other useful things. Finally, Ostendo is working on a light field streaming protocol. When we imagine a visual experience that allows us to naturally adjust our focus to objects that are near or far, across not just 1 or 2 focal planes, but many planes, we're effectively recreating light field information. That requires a tremendous amount of data. Ostendo is working on a viable approach to compute and compress that data for use in wearable glasses. Let me leave you with one last thought. As I shared in the early slides, display technologies take time. The industry isn't going to jump straight to an idealized final solution. We have to walk before we run. Within the consumer arena, I imagine the next several years will follow a similar trajectory to feature phones and smartphones. We went many years, decades really, where the primary purpose of the mobile phone was to enable communicating with anybody from nearly anywhere. The smartphone, when combined with GPS and wireless data, enhanced that just-in-time coordination ability and extended it to be a good, or at least a good enough, content consumption and creation device. Feature phones started with a core value that billions found useful, and that value expanded over time. For wearable AR glasses, the core value is to deliver hands-free, just-in-time contextual insight. That doesn't mean 3D digital content that fully immerses us in an alternative version of reality, it means a device that, in coordination with our smartphone, has sufficient awareness of what's relevant to us in this moment to deliver timely insights, and do so much more quickly and conveniently than pulling our phone out of our pocket. We'll get to highly convincing altered realities, but that's not the first step. Ostendo is laying the path, putting forth the most critical ingredients, both for what's needed today and for the long future of the coming photonic era. Thanks for listening. I'm happy to take some questions now.
Hey, welcome back. I'm Joshua Ness. I'm the track chair here for XR Enablement at AWE Online 2020. Here with Jason McDowall, who just gave us a really great presentation on his company Ostendo and some of the amazing technologies that they're working on. Jason, great to have you here.
Yeah, thanks.
Yeah. So it sounds like there are it sounds like some really great advancements in reducing the form factor of AR and really unlocking some potential, like you talked about. What are some of the industries and use cases that you see that might be first or early adopters of what you're building over there at Ostendo?
At some level, as I kind of showed in that last slide, my perspective is that we're on this long path ahead of us. Like, we're not going to jump straight to having this fully immersive alternative reality. It's really going to start with having information that is just in time, highly contextual to that moment, hands-free being key. And places where that makes sense, I think, are the places where we're going to see the earliest adoption. And that's true whether it's in an enterprise sort of setting or whether it's in a consumer sort of setting. And so the scenarios you can imagine where you need your hands to do something else, those are the places where I think that we're going to see this sort of display on your face, wearable display, really begin to take off.
Yeah. Do you see connectivity playing a role there for users to be able to use that technology while they're working with maybe having expert come in and be able to guide them through a project?
Absolutely. Both connectivity in the personal area network sort of things, depending on what that configuration of the device is. I'm a big believer that the smartphone is going to be a companion device to the glasses, certainly for the consumer arena. So yeah, that local area connectivity is necessary, but absolutely you need the broader area, wide area network connectivity as well. We're not just talking about streaming video back and forth and potentially, doing off-device rendering and that sort of thing, but we're also talking about an evolution over time of presenting a deeper, richer visual experience that includes multiple layers of depth of that digital information, a light field sort of thing, and that's going to require a significant amount of data as well.
Yeah. How do you see the form factor evolving with the evolution of things like edge computing, being able to pull some of that compute off the device when connectivity with something like 5G is advanced enough to enable real-time off-device compute? How do you see this technology evolving there?
That's an interesting question. I think that from the head-worn component of it, right, we're trying to get as small as possible, right? We're trying to get 65 grams less so that it's really comfortable, because that weight rests just on our bridge of our nose or on our ears. And to the extent that we can offload that compute necessity, the compute needs of that device, it's really important we do so. And that might be locally to the phone, but it'll ultimately also be to the edge. But I also point out that at least as it relates to the device that is in your pocket, not necessarily on your face, but in your pocket, we've seen in some ways the opposite trend. In part driven by our desire to have a more immersive visual experience, right? That first iPhone you showed in your presentation was much smaller than the one that we carry around today. And that's because it's primarily driven by longer battery life desires, the higher network needs, the battery utilization of the network, bigger visual screen that requires more battery, and we want that larger field of view. So it's interesting. I'm not necessarily sure that the pocket device is necessarily going to get teeny tiny with 5G. We're going to find ways to use all that data in other more useful ways. But we'll see. Certainly on the head, we want to make that as small as possible.
Yeah. I think that'll be interesting. I think the ability to pull compute off of a variety of devices will lead to an evolution in form factor. Not the least of which might be things like that personal device even evolving into something of an ecosystem approach where some of the technology that you're developing might play a significant part. So I think that's pretty neat. There are some questions in the chat room. A lot of them about people want to know when they can get their hands on it. Things like time frame and pretty much when do you think something like this will be available? I'm sure that you do you have any response to that, or is that still something that you're working on?
Yeah, I can talk a little bit about that. The QPI, the little displays that I showed in the video, were made at our nanotechnology lab near our headquarters in Carlsbad, California. And in making those, we used standard semiconductor tools, but there was a fair amount of kind of manual handling and adjustments that were in that process. That said, those displays are really stunning in person. But to support our customers, we've recently started the process of building a pilot production facility near our headquarters. And when complete, that pilot production facility will be enough to supply our initial production needs of our strategic partners from that facility. But of course, the ramp up, the long development cycle that goes into actually creating a pair of devices that are manufactured at scale and sold, that process starts well in advance. And so to support those efforts, we will be providing engineering samples later this year.
Nice, very cool. We'll look forward to that. Lastly, for people who want to get in touch with you, how can they do so? Can they reach out to you on social media, or how can people continue the conversation?
Yes, social media is definitely a channel, although I'm a little bit slow to respond there. I will drop my email into the chat on the right here in just a second.
Sounds great. I think there are a couple more questions in there around power consumption and the display technology as well. So please do take a look at that. So thank you so much for Jason McDowall for that inspiring presentation and for sticking around to answer some questions. And we'll see you around.
My pleasure. Thanks, Josh.